Hey there, and welcome to this explainer. Today, we're diving into a totally foundational concept in object-oriented design. When we set out to build massive, complex software systems, we aren't just writing one giant, endless block of code. Instead, we're designing objects out of smaller, hyper-focused components. It's kind of like snapping together digital Lego bricks or assembling the tiny gears of a really high-end watch. But here's the catch. The way these components actually relate to each other, it literally changes everything about how our software behaves. So today, we're going to masterclass relationships by breaking down the difference between tightly coupled composition and looser aggregation. All right, here's our roadmap for today. 1. Building complex objects. 2. Composition, which is all about strong ownership. 3. Aggregation, dealing with loose connections. 4. The ultimate OOP showdown. And 5. Avoiding common mistakes. Let's jump right in. Section 1. Building complex objects, moving from monoliths to modular design. Now, right off the bat, I want to pose a bit of a life or death question to you. Think about this. If a computer program is deleted, do its internal parts disappear right along with it? Take a second to really chew on that, because the answer to this question actually defines the entire architecture of your code. It all boils down to object life cycles. So why break down complex objects in the first place? Well, modular code is basically a developer's superpower. Think about it. By isolating components, like letting a laptop's battery just handle power while the screen just handles the display, your code instantly becomes so much easier to read and understand. And because you've got these isolated components, they can be tested totally separately. The responsibilities are crystal clear. That makes the whole program vastly easier to maintain, debug, and upgrade over time. Section 2. Composition, strong ownership, the tightly coupled relationship. Let's meet our first contender. By definition, composition is a strong relationship where an object is built from tightly coupled component objects. The parent creates and absolutely owns the parts. You can think of composition as the ultimate micromanager. It's a slightly clingy relationship, to be honest. The parent is the absolute unquestioned boss of its subcomponents. Let's look at the main characteristics here. The parent creates and owns the parts, which means the part objects are intimately tied to the parent's lifecycle. Without the whole, the parts hold literally zero meaning on their own. It's a super strong part-of relationship. Oh, and if you're looking at developer blueprints, this tight, unyielding bond is stamped with a filled diamond in UML. A perfect way to picture this is a house and its rooms. A house is composed of rooms, right? Demolish the house and the rooms go down with it. That is the absolute essence of tight coupling. A kitchen or a bedroom just floating around in a digital void makes absolutely no sense without the house that actually contains it. Section 3. Aggregation. Loose connections. The weaker has a relationship. All right, take a deep breath because we're shifting gears from strict ownership to loose grouping. Aggregation is defined as a weaker relationship where one parent object just groups or uses other objects that can continue to exist completely independently. The absolute crucial differentiator here is freedom. In aggregation, the parts have a life of their own. They're just visiting. So here are the main characteristics of aggregation. The parent refers to but doesn't fully own the parts. Because of this, the part objects can totally outlive the parent if the parent is ever removed or deleted. It's a weaker has-a relationship, which is actually fantastic when you need to reuse components elsewhere in your program. And because this bond is way less permanent, UML uses a hollow diamond. Think of it as an empty space, leaving room for those parts to pack up and move somewhere else. Let's see this independent life cycle in action. Picture a sports team and its players. A team aggregates players. If that team dissolves, goes bankrupt, or just gets deleted from the system, the individual players don't just magically cease to exist. No way, they stay independent. They basically become free agents. They can transfer and join a totally different team. They're grouped together temporarily, but they are not bound by life or death. Section 4. The ultimate OOP showdown. Composition versus aggregation. It's main event time. Conceptually, both of these describe whole-part relationships, but they are on totally opposite ends of the spectrum. Composition is your internal creator, a strong part-of bond featuring tight coupling where the parent handles the creation. Aggregation, on the other hand, is your external collector, a weaker has-a bond featuring loose coupling where parts are usually created externally and just passed in. When you put them head-to-head in a matrix, it really all comes down to survival and independence. Composition strongly owns the parts, and they die when the whole dies. Aggregation merely groups the parts and lets them walk away if the whole goes down. It's tight coupling versus loose coupling. And visually, you've got that filled diamond for solid ownership versus the hollow diamond for flexible grouping. To make this super concrete, let's look at how code syntax actually reflects the design. In a Python composition example, a car class creates the engine right inside its own initializer block. The car entirely owns that engine. But in a Java aggregation example, a team takes an existing list of player objects that were created completely outside the class, and they're just passed in via the constructor. So the syntax perfectly mirrors the relationship. Section 5. Avoiding common mistakes. Navigating the pitfalls of OOP design. Let's save you some serious debugging headaches. Understanding the theory is great, but applying it is where folks often trip up. A huge mistake is assuming that just because a class holds another, it automatically owns it. Mere containment is not true ownership. And remember, has-a is very different from is-a. A car has an engine, it isn't an engine. Don't confuse your inheritance with your composition. Also, drawing the wrong UML diamond or sticking it on the parts side instead of the whole side is a classic mistake that's going to confuse your entire team. To flawlessly identify the correct relationship every single time, treat this 3-step process as your ultimate checklist. Step 1, check ownership. Who creates and controls this part? Step 2, check life cycle. Does the part survive if the whole disappears? And step 3, check reuse. Can the exact same object realistically belong somewhere else in your system? Okay, let's test this out with a quick scenario from some school software. Scenario A. A school class contains a seating plan. That plan belongs to that class only. If the class is deleted from the database, the seating plan gets deleted too. So, what relationship is this? Take a guess. If you just yelled composition at your screen, you absolutely nailed it. The seating plan is tightly bound to the school class. It has 0 independence, so its life cycle is entirely tied to the parent object. All right, round 2. Scenario B. A department has teachers. If the department closes down, the teachers still exist in the school system and might just get moved to another department. Which relationship is this one? It's aggregation. The teachers can just pack up their desks and survive the department closing. Because they survived the destruction of the parent, they exist completely independently. The department was merely referencing them.
We've covered a ton of ground in this explainer today, from monoliths to modular architecture, tight coupling to loose connections. As you go forward and design your own classes, if you ever find yourself staring at a blinking cursor, wondering exactly how to link your objects, I want you to step back and ask yourself this one ultimate diagnostic question. Can the part exist alone? Your answer to that is going to unlock your entire software design. Thanks for joining me, and happy coding!